The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. This is Kevin Humanick. Welcome to this month's webinar for Sustainable Labs Canada. Thank you for attending. Today, we have Gordon Sharp presenting his presentation on reducing vivarium energy use by up to 50% with the new CCAC air quality and air change guidelines. Just a moment to kind of let you know that if you do have questions during Gordon's presentation, please record them in the question dialog box. Feel free to submit them in writing, and I'll relay your questions near the end of Gordon's presentation so that he can respond to them verbally. So as he's presenting, feel free to submit your questions, and I'll relay them at the end. So by way of introduction, Gordon Sharp is the chairman of Aircuity and has over 25 years of experience and over 25 patents in energy efficiency, indoor environmental quality, and laboratory controls. As the founder and former CEO of Phoenix Controls, he led this world leader in laboratory airflow controls that was acquired by Honeywell in 1998. In 2000, Gordon founded Aircuity out of Honeywell and is a smart airside energy efficiency company. Gordon is an MIT graduate, an ASHRAE distinguished lecturer, and the executive vice president and a member of the board of directors of I2SL, the International Institute of Sustainable Laboratories. He's also a voting member of ASHRAE Standard 170 on healthcare ventilation and the ANSI Standard Z 9.5 on lab ventilation, as well as a member of the ASHRAE TC 9.10 Committee on Laboratories and the TC 9.11 Committee on Clean Rooms. So thank you, Gordon, for being here today. And without further ado, please take it away.
Great, thanks, Kevin. So again, what we're going to talk about today is sort of reviewing a little bit of control on how it can reduce energy in lab, but also about the new CCAC guidelines, what's changed, and what they're now allowing in terms of what can be done in Canada. So I just throwing up some like this type of technology is being used, but again, we want to just get to the presentation. So basically, what I want to get into again is a little bit about demand-based control, into a little bit of the guidance from both the U.S., CCAC, ILAR. More, it's the sort of details about the guidelines, addendum next year regarding that. Search on demand and some of the supporting committee moved the way it did, and then a little bit about the economics and why it makes sense for people, particularly, I think, up in. So that in mind, let's get into a little bit about this. So I want to reduce energy in vivariums. The key driver for the HVAC system, it's 60 to 80% of the total of a vivarium is the HVAC. Regarding the high ice facilities, it's definitely the anything else by a far margin. And that air change rates that is required in vivariums, at least. Now, with the new guidelines, they're into the issue of air quality within and encouraging the use of monitoring for that, but also that if you want to reduce the energy use in the vivarium, then constant system that reduces on the measurement of, again, with that, you can both dramatically energy use, but also HVAC capacity and also the first cost. And it wasn't before, but now it is allowed with the new guidelines, which we'll get into. So again, a little bit about, vivariums and obviously so the respect. I think it's always important to sort of understand and get grounded on hires and what's for the airflow requirements at these different levels and how is it controlled. And again, what we have is three more airflow within these facilities, vivarium or lab. We have, these exhaust requirements. It could be biosafety cabinets, could be from the animal. These device airflow, and as a result, they appear compensate. That one requirement based on the amount of devices. You can change based on what the devices are doing. If we're going to be animal racks, we have racks or less, or they get building or affect the airflow as well.
Hi, Gordon.
In addition to that, we have a thermal.
Maybe I can interject just really quickly, Gordon. We're having a little bit of distortion in the audio in your presentation. Is there a way that you could, just wondering if you're currently dialed into audio by phone or if you're connected through computer-based audio?
I'm using the phone-based audio.
Okay. And are you in a voice over IP system?
Just a regular cell connection.
Interesting, because the audio seems to be garbled at times, but right now you sound fine. So maybe what we could do is continue, but it does seem that it's getting distorted off and on. So we'll monitor it, and I might have to just interject to see if we can source a different audio connection, or maybe switch to computer-based audio if it continues. So let's continue.
Yeah,
We'll see.
Okay, yeah, definitely to the problem. So.
Yeah, I mean, is there a way maybe for you to switch to computer audio at this point and see if that fixes it?
I think so. Let's
yeah.
Take a look here. So I think
under the audio dialog box.
Okay, so now I'm working with the computer audio. Can you hear me?
That's a bit better. Yeah, thank you. Sorry for the interruption.
Yep, no problem. So again, if it's not coming through, let me know, but we'll try it like this way. Okay, so as I was saying, we have these three requirements for the airflow within the lab: the fume hoods or biosafety cabinet, the animal rack, the exhaust for that. We have to provide a certain amount of airflow to maintain or make up the air for that. We have the thermal load, where we have to obviously handle the thermal heating, obviously the cooling requirements for the facility based on the animal loads, etc., which we'll talk about in a second. And then lastly, we have the dilution of ventilation requirements, which again in Canada have been 15 to 20 air changes in vivariums is basically the requirement. So the point of this is that whichever of these three requirements is higher is what dictates the airflow. So if we want to save energy and reduce airflow, then we have to reduce all three of these. You know, we can reduce airflow in one or two, but if the third is the highest, then the airflow is going to be the same. So we have to affect all three of them. Now, obviously, in terms of a vivarium, we have we have certain racks. Some of those racks have varying airflow requirements. So we have a requirement for that, but typically that is not a driver for the airflow within the vivarium. The other aspect can be the requirements for the thermal load. So let's just take a look here. So we have the thermal load requirement, and again, in that case, typically when you look at animals, and even with ventilated racks, you have a requirement for typically in the range of about 4 to 8 air changes. Again, it depends on the racks and the density, but that typically is the requirement. Sometimes people think that the rack, since it's exhausting air, even if it's exhausted directly into the ventilation system, that takes away all the heat. But actually, most of the thermal load is due to radiation from the rack itself. It's not, you can't get rid of it by just exhausting some air. I mean, it helps a little bit, but most of the load goes right into the room. So typically for these spaces, again, to cool the space based on a typical animal loading, you're in that range of 4 to 6. So we won't be able to get below that. So we're going to obviously reduce airflow, but we obviously have to provide at least enough airflow to maintain that thermal load, the cooling requirements. Now, non-animal holding areas, obviously in a vivarium with many different rooms. We have the animal holding rooms. We also have rooms for surgery, for different aspects of the engagement of the animals, different things that can, cage washing, etc. So in these spaces, we don't have typically that high a load, so a thermal load. So in those cases, we can reduce it down to maybe in the range of 2 to 4 air changes. Again, the driver for airflow in these spaces has traditionally been the ventilation requirement, and that's where demand-based control comes in. And the idea being that the reason we have these requirements is due to the potential for pollutants, for contaminants, particles, particulates within the room, ammonia, VOCs, volatile organic compounds. So that point here is that if we can see when the air is clean, which it turns out in vivariums is very high, typically in the range of 98%, or for some spaces maybe 96 or maybe 99, but it's in that very high level. Most of the time the air is clean. It's just that things can happen, and things do happen from time to time that require the greater airflow, which is why we have it. But again, the point here is that if we can sense the contaminants, and when the air is clean, then we can obviously reduce the airflow. When basically we need that airflow, then we want to go up to the 15 to 20, which is typically recommended. But obviously, if the air is clean, we can drop to the lower levels. Typically going to be set by, could be the rack requirements, but as I mentioned, it's probably more likely the thermal loads are going to be setting that sort of in the range, as you see here, maybe 4 to 6 for the vivarium airflows. For the non sort of holding areas, again, could be lower in the range of 2 to 4 air changes. So that's the basic concept behind demand-based control. The question is that allowed? What's been the recommendation around this? Oh, and one point here, just to show a little bit about the action for this. So you can see here, this just shows a typical situation. This is from a vivarium, and you can see the magenta line at the top is showing, some excursions related to some things that were happening in the vivarium rooms. So you see some happenings, and then obviously what is going on is that demand-based control. On the bottom curve there, you can see the blue line is picked up on this and has increased the airflow to compensate, to basically provide a purging event to basically clean out the airflow. So you can sort of see the action of the airflow relating to the contaminants. Okay, so again, in addition to saving energy, there are other benefits to sensing IQ in vivariums, and a lot of it relates to understanding what is that environment. Obviously, in a research situation, we want to control variables, so IQ and the air quality within the space can have an impact on the animals, which obviously can have an impact on the research. So it's very important to maintain a clean environment, obviously for both ethical reasons, but also for research reasons. So for that aspect, monitoring the air quality allows us to assure us that we have a good environment, or if things go wrong, then obviously we can diagnose those things quickly, we can understand there's an issue, determine it, and then resolve it. So again, the idea here is that monitoring air quality allows us to ensure that the air quality will be good, because we now have direct feedback of what's happening, whereas typically we don't. You might monitor for air changes, you might monitor for pressure, maybe lighting, but again, not directly the airflow or air quality, which is obviously such an important factor. And again, it's not just the animals. Obviously, part of the reason for why we have this airflow is also for protection of the people. One of the obviously big concerns here is allergens within the space and people getting sensitized to that. So we obviously want to detect that and make sure that the air quality is good and people will be protected from those contaminants. And again, the other aspect here that sometimes it's used for as well is to look at how often the cages should be changed. So if we typically the reason for the cage change is to prevent the buildup of these sort of ammonia and allergens within the space, and this provides one way of directly seeing what's happening, and then as needed be able to optimize the cage changing frequency and how that's done. So there's potential labor saving there, and also just another way to improve the air quality. What I have here is just some diagrams showing the type of things that can happen. This is some non-human primate cage changes that you can see we're creating significant particle spikes, basically relating to the fact that we're cleaning the cages, and you can sort of see not only the particle levels go up, but obviously the humidity go up as they were washing the cages. So this, obviously during those periods, we would be increasing the airflow. You can sort of see that in this diagram, where you can see the airflow is spiked up to basically try to purge the space. But In these situations, again, the air quality monitoring is helpful because even though we're providing greater airflow, the intensity of the particles is pretty high. So at that point, you probably would be recommended to use some PPE equipment, some protection equipment for the employees, just to make sure they don't get overly exposed during those cleaning processes. So again, not only can we control the airflow, but we can again provide some feedback that might improve operations and improve the safety for the operators. So again, what we have now is some information on the guidance around other areas in terms of this aspect of demand-based control. And actually, since 2011, has been recommending this concept both for labs and vivariums. This is the guidance specifically related to laboratories. Again, they use the term real-time sensing of contaminants. That's their word for it. My word is demand-based control, but exactly the same thing. And again, it talks about, at least in laboratories, going down as safely as 2 air changes per hour, obviously when the lab air is clean. So when we get to the vivariums, we have sort of different people weighing in here. ASHRAE again weighs in again with a recommendation around the use of this, again, as they call it, active sensing of contaminants. They refer to the secondary enclosure, which is the room. And again, obviously, based on that, you can vary the air change rates. ILAR, since 2010, has been recommending the concept of varying airflows based on not only heat load, but other variables, such as air quality. So that's been in place for some time. ALAC, which works off from ILAR, again, also allows us and has been actively recommending the use of this concept, again, allowing you to go below the 10 to 15 air changes. And again, part of this is that there's been a drive towards performance-based criteria, as I have there in the slide. And that's really what happened is ALAC is moved away a little bit from the prescriptive and says basically trying to focus not just on air quality, but in other areas as well around performance-based criteria, that if you can achieve the end result, then you don't need to be prescriptive. You can allow for other concepts and approaches that can provide a more optimum approach as long as it achieves the intended results, in this case, air quality. So for some time, this has been the case. Now, in Canada, that has been not the case. And in Canada, a little bit different from the U.S. and some other areas, there's been more of a mandate around air changes. Now, actually, this is sort of from a global standpoint, the other area where this is true is also the UK. So the UK has very similar guidelines to what Canada has had around this requirement for this 15 to 20 air changes. I don't know why those are probably related to maybe some focus on the two countries, but in any case, this has been the case in both the UK and Canada. Now in Canada, actually here I have on the slide, you can sort of see not only is the requirement for 15 to 20 air changes in terms of the airflow, but also the systems, the HVAC system has to be capable of supplying 15 to 20 air changes in each of the spaces. So that has resulted in large HVAC systems that can handle this volume of air, which is obviously going to be needed, even if the room isn't being used. Obviously you don't know when that's going to be, so the HVAC system has to have that capability. And in case, as you can see here, that it's even saying that sometimes you may need more than that airflow as well. So this has been, basically been the requirement for up to really this year. And based on this, there was a movement beginning about 2010, based on what had happened with ILAR, based on what ALAC was then recommending, and sort of seeing this concept being used. Up in Canada, with the CCAC, they started a movement to look into this. And one of the concerns was to be a little bit more prescriptive around it. If you notice what ILAR and ALAC have said, it's more performance-based, but it doesn't list what the performance is. That's sort of up to the local facilities to basically determine that and then maintain that over time. So it's sort of like a quality guideline that there's not specific aspect of what the quality is, but whatever you're going to pick for your requirements, you have to maintain that. Now, what the CCAC wanted to do is said, well, we want to be a little bit more prescriptive around that. We want to set up what the performance guidelines are, and then based on that, as long as people meet what those performance guidelines are, then obviously they can use what airflow they want. So it's a little bit different than, let's say, ALAC or ILAR, which leave it much more general. Again, the CCAC wanted to be more specific. So beginning in 2010, there was a move to investigate this to understand what were either the recommended levels or the levels of air quality that would be prescribed, and then based on that, obviously the airflow could be varied to meet those requirements. So this started in 2010. Started, frankly, a little slowly, but began to get momentum. It had different, some drafts came out, some feedback came back, and so it went back and forth several times. And then I personally got involved. I was involved in the committee from just a commenting standpoint, but then there was some changes, and a few people left the committee, and there was some openings, so I got involved myself personally around, it was like 2015 or so. But the point of this was to, and there was one other person who was added as well. And at that point, things sort of picked up steam a little bit, and basically began to get more specific around what the requirements should be. And then again, some more public review drafts went out, and the result of this was in 2018, sort of mid-2018, the draft was finished. It then was approved by the CCAC board, and then finally, in February of this year, the final publication issued. So, so again, a lot of this was not a quick process. Obviously, it took about 90 years over this whole thing, and obviously very well considered. A lot of input was brought in from many different sources. Again, 3 public reviews, many peer reviews. So I think it was a well-vetted document. And so what we have now, if we can start to get into some of the details, and this is, you can see the draft, it's available publicly from the CCAC, so you can freely download it. They have not only the guideline, but then they have a nice little FAQ section or document as well. It's a sort of a separate document. There was a lot of questions came up during the public reviews, and as a result, we thought it would be very helpful to have not in the standard itself or guidelines, but to have a separate document that would give some other information that might explain a little bit of why some of the different levels were chosen, and just other information about the standard. So if you do download the standard, definitely also download the FAQs. I think those will be helpful for you if you have any questions. Again, I'm also, of course, happy to answer them later at the end of this webinar. So again, so this is where it came. You can see the different people involved. Don McKay was the chair of the committee. Chris Krausgrove was also involved. Wilma Lagerref from Memorial University. Ken Gugrel from Global Affairs, basically Public Works, and of course myself. So the official position, when you get down, was really that and again, what this was is an addendum that adds on to and modifies the document, the original document, and basically was addressing the guideline number 96, which relates to this issue of the 15 to 20 air changes. So the idea really was that we would allow the reduction from 15 to 20, but only if you basically provide this monitoring and control of the airflow. But at the same time, a lot of the standard, a lot of this guideline or addendum focuses on air quality and the recommending the monitoring of air quality, even if you're not going to reduce the air changes. So it's just a good practice that was recommended. And as you'll see, we talked a lot in the standard about what is good air quality, and of course how to some ways to monitor it and provide that good air quality. So one of the things that came up when we were doing this addendum was to try to understand, what is the cause of poor air quality, or what are the causes of things that can happen within a vivarium space, which relate to, number one, why we should be monitoring in the first place, but also why do we have the air change requirements. Sometimes people have said, gee, we've got ventilated racks, they're going to clean, they keep the contaminants out of the space for the most part, and why do I need higher air changes? So we thought it was important to sort of lay out what we believe were the sources of these contaminants, where do these come from, and we sort of broke down into 3 different areas. We generically labeled them systemic, operational, and episodic type situations. So what I mean by that is, or what we meant by that, was the fact that systemic issues relate to sort of the sort of system aspects. They relate to the design and the maintenance of the facility, the HVAC system, how the system is being used. So this would be, for example, the type of enclosures. Is it open cage? Is it ventilated racks? What type of exhaust configuration? Is it relate to a direct exhaust? Is it exhausting into the space, etc.? So those were, first of all, things that affected the air quality, and hopefully, those are designed well so that it creates a clean environment. You then have operational issues. Okay, so how do we operate the facility? What are the standard operating procedures? What's the type of animals we have? What's the density? What is the equipment we have in the room? Are we using cage change stations, for example? How do we change the cages? So all these can obviously impact air quality depending on how they're done and performed. The hope is that in both these situations, you can set these up to provide, primarily a fairly clean environment. One of the biggest concerns, though, related to the last factor, which we call episodic. And frankly, this is sort of in the category of sort of stuff happens. So it's, you do the best you can, and then things happen. So the result of this is that these don't always happen. They can't be predicted. They're not necessarily related to the fact you have good systems or operational approaches. But again, things happen. Maybe the training on someone isn't quite effective. Someone begins to forget his training, or isn't applying it properly. Just classic human error. Equipment that breaks, equipment that fails. I mean, things like this can happen. And again, because of the situation we're dealing with, where the quality of the air is very important in this facility, again, both for the level of research, but also for protecting the individuals. These are concerns. Again, typically what you find as well is that these things can be very short in duration. And again, as I look at data that we've monitored this stuff for many years ourselves, you see these sort of things, these little episodic events. That tends to be what tends to generally be happening. It's not the long type failures or related to the systems. It's things like that generally are detected and cleaned, or basically resolved. But it's these shorter things that happen that may not always be seen if you're not monitoring things continuously. So this is sort of where the monitoring becomes important, to sort of catch these sort of things and then resolve them. As an example, as I mentioned earlier, sometimes with ventilated cages and good SOPs, you might think you're in a good situation, and hopefully you are, but it still can't eliminate these episodic events. Maybe someone drops a cage, maybe a cage change station, the filter, breaks through or something because it wasn't changed as often as it should. Again, different things can happen, and that is why a lot of times we need that air quality, we need the high air change rates. So this has sort of been one of the aspects of why this came about and why the airflow rates were set high to begin with. So based on that, the committee said, all right, well, with all this in mind, what are the different ways that the Vivarium could be operated, and how can we provide a means potentially to save energy by reducing flows while still maintaining good air quality? And we came up with these three different sort of scenarios of how or modes of operation that the Vivarium will be operated. So in most situations, you're going to fall into these three categories. So the first one obviously is what we've done before. It's constant flow, no IQ monitoring. In that case, the committee is saying 15 to 20 air changes that applies. The recommendation is it's good to do some form of IQ monitoring, but it's not required. I mean, it's sort of the status quo, I guess is the way you could put this. So, which is fine. I mean, people can continue to do what they're doing, not a problem. The second category is that we do apply some form of IQ monitoring, and although we're not changing the flow rates. Now, what the committee has said is that can allow some reduction in air changes, down to about 12 air changes. But it does require IQ monitoring of some type, and basically that type falls into these two categories of IQ monitoring that we specifically laid out in the document. One is obviously straightforward, is the continuous monitoring. In that case, we're basically picking up samples or monitoring the air quality in the space at least every 15 minutes and doing that on a 24/7 basis, obviously recording that data and allowing it to be reviewed and monitored. The other aspect that we laid out is if someone didn't want to put in a continuous system, there are another approach, which is sort of a periodic approach, but it's sort of a long period. So basically what it says is that when the system is initially set up, when the facility is opened or at least changes occurred, that the spaces are individually monitored for a continuous period of about a month. So basically you could take a portable instrument as an example and put it in the room and basically monitor for a month continuously with that device. And at the end of the month, you could move it to another room or have maybe 20 devices you lay out. So basically, says you don't have to monitor all the time, but you do need to monitor for at least that 1 month to verify that the systems are working correctly. And then it also requires a sort of a checkup every 6 months for at least a period of 2 weeks for each space. So pretty heavy amount of requirement as well, but not necessarily full continuous monitoring. So the committee wanted to provide another option for those that didn't want to necessarily put in a full-blown system that was monitoring all the time. So that is available, and it can be used for this sort of intermediate aspect of being able to go as low as 12 air changes, down from the 15 to 20. Now, for those that want to achieve greater energy savings, then obviously we get into the final category, which is the classic demand-based control, which is now a variable flow control based on the IQ monitoring. So at this point, there's no prescriptive lower limit. I mean, technically, you can operate at any level you want as long as you're maintaining good air quality. That's the only requirement here. And again, as I'll get into in a second, those levels have been set out. So this does require monitoring then at least every 15 minutes on a 24/7 basis, and also requires the use of that information in a real-time air quality control, flow control basis to maintain that air quality, maintain it good. So with this now, you have the ability to provide significant savings and full monitoring of the environment. Okay, so with that, let's get into the actual guidelines that were laid out in the document. So there's a bunch of guidelines. Guideline 1 basically begins to lay out, how this thing works. And so this basically states that the institution allergens, being able to get at that information. And lastly, for total volatile organic compounds, solvents, other sources of obviously chemical vapors in the space. So basically, we lay it out. You can see we have a target value of what we're trying to achieve in the airflow going into the space, so you can see what those values are there in the table. And then we also provided what we believe should be the values in the space, and we provided that both for target value that we're trying to achieve and also maximum value. So the idea would be is that, generally within normal operation, we're trying to maintain levels, at or below the target value, with the understanding that at times you may get excursions, which is obviously when you probably want to provide full airflow, and then you'd hope that you'd be returned back to the target value and not exceed the maximum values. If the maximum values are being exceeded, then obviously something's probably wrong, not with your airflow, but with, well, could be that too, but probably there's other issues in terms of the design of the facility. It gets back to those systemic or operational issues that are causing these values outside those levels. Normally the airflow should be able to get you back in if everything is working correctly, if you have the right setups. So again, that's the thing. We lay out these target values and maximum values, and then we also laid out how some methods of measurement, because some of the values, particularly like for VOCs, will vary, total volatile organic compounds, will vary based on the type of instrument or the system. So we were very specific about that as well, and allowing different approaches and recommendations around how that can be done or how those levels could be measured. One other thing I just want to go back to. The other thing that's important to note too is that a lot of these values are differential values. They're not necessarily absolutes. Many times the maximum value is listed as an absolute, but most times the target values are differentials. And the reason for that is that you are going to have sometimes some contaminants like, well, obviously particulates or VOCs that can occur sometimes in the supply air, and obviously in that situation the dilution ventilation is only going to provide as good as you have for the supplies. So in this case we're referring to differential values, particularly for like CO2, actually both the particulates and VOCs. So we're going to look at the levels in the supply, we're going to levels in the exhaust. That difference is what we're going to try to maintain at least at the target value. So I think it's important to understand that some of the values are absolutes like the maximums, but others like the targets are differentials. Okay, so basically what we have here is some more of the guidelines. Now we're getting a little bit more specific. Guideline 2 relates to that we can operate at lower than the 15 to 20, but again, you need to monitor and record the air quality contaminants, and then as it puts here, ensure mechanisms in place to correct the deviations, which again would typically be related to an airflow control means of increasing airflow. Number 3, we started to get into the more of the specifics, getting into the contaminants. Again, as I mentioned before, it's ammonia, carbon dioxide, particulates, and of course VOCs, total volatile organic compounds. Then the guidelines get more specific now into talking about the levels again, which is sort of what you saw earlier. For ammonia, again, we want to maintain it below 25, but in general not exceed 5. CO2, we want to keep it below 500 ppm. Particulates, we have there the 12 micrograms per cubic meter, basically relating to a 0.3 micron channel. And then VOCs, you see, is in the range of 500 micrograms per cubic meter. Some of these measures, like the 500 micrograms per cubic meter, or equivalently 200 parts per billion, relate to levels you would see for like the LEED requirements for flush out in office buildings. So it's a pretty clean level that's being recommended here, but I think one that's definitely achievable and easily achievable, unless there's some problems with the systems. The other aspect was the capacity. So again, the other aspect of this guideline is to opens up the ability to now design a system that doesn't necessarily have to run, it doesn't have to be designed for all the rooms running at 15 to 20 air changes. Obviously, with a sort of demand-based approach, some labs, some areas, some Vivarium areas, holding rooms may operate at the full airflow, but it's highly unlikely that all would run at the same time at that level. So this, the guidelines now open up the opportunity to apply diversity factors that allow you then to reduce the size of the HVAC based on how you expect the system is going to run, what you're, based on thermal loads, etc. So it's similar to how this is done in laboratories. This is now allowed, whereas it wasn't before. So now you can reduce this down. Obviously, you need to analyze this and look at it carefully, but there's definitely some opportunities now to reduce HVAC equipment sizing for these spaces. Okay, so that sort of gives you a good, I think, an overview of what the guidelines lay out. What I wanted to do here is, again, present just some of the evidence and data that was used by the committee, sort of in terms of coming up with some of the numbers and values. As an example, this is some data from the University of Pennsylvania. They were looking at, they had a situation with open cages. They had thought about, let's see how we can, if we can reduce airflows and improve that. And you can see here that they originally were running at 19 air changes. In this first week, the data, they basically brought the airflows down from 19 to 10, and then measured the ammonia levels at the near the end of the cage change cycle to see what was happening. And as you can see in the column there on the first week, the levels were high and noticeable. Obviously, were creating problems. So it sort of verified that yes, the 19 air changes was necessary, which again provides support again for why this level of 15 to 20 has been out there for so long. But then in the second week, they applied a demand-based control approach, which then applied airflow when needed to keep the odors down, prevent them from building up. And obviously, you can see it worked quite well. So again, this obviously provides some of the basis for this concept. And you can see this is just showing some energy savings. Obviously, they achieved significant savings in this case. It was 42% over the whole facility, and the animal spaces weren't obviously the whole facility. So again, quite a significant reduction. Dr. Brammer's done some research on this. He has some systems, both with non-human primate as well as animal facilities, and he had 2 rooms. He set up both cases the rooms were operated for 30 days with both constant flow control at 12.75 air changes, and then also 30 days with demand-based control running at 4 air changes and a purge at 20. And the results were that you could find no appreciable difference in the air quality for both the constant airflow or the demand-based control operation. He did have times when the system needed to go to higher flow, up to that 20 air changes, about between 1 and 5% of the time, based on the type of rooms there. But again, obviously, it cleaned the air and kept the air quality good. Obviously, significant savings were achieved by being able to reduce their airflow rates. Another example of this was the Memorial Sloan Kettering facility down in New York City. A very large project, both labs and Vivarium. Basically significant energy savings, even got a large rebate from Con Ed. So supplied a very large project at a large scale, obviously quite successful. So again, obviously this has been used before. I mean, again, it's been used around the world, many different areas. The exceptions have been, as I mentioned, both the UK and Canada because of the requirements that have been in place in the past. So just the last thing I wanted to mention is a little bit on the sort of economics of this, and again, as I've mentioned at some of the other SLCan conferences in the past, we have a nice tool we use for analyzing energy savings in labs and vivariums. So just to give you an idea here, I used that tool, this ROI sort of energy savings analysis tool, to look at that for a vivarium. So in this sort of typical situation, I've got a 30,000 square foot vivarium. That's so net square feet in terms of the animal spaces. So in that way, I've assumed I've got 100 rooms at an average of about 300 square feet. I've got a baseline situation of with 15 air changes, and I'm assuming that we're going down to sort of 6 occupied, 4 unoccupied. However, sometimes we're going to be higher than that based on the thermal load, so I'll mention that in a second. And again, in this case, I use Boston for the weather data, just as a convenient location. So again, in this case, I got the room temperature set to 74. We got some other assumptions about energy costs. In vivarium, we typically have humidification, so it adds a significant increase in cost. So I've got steam humidification. And then, as I mentioned before, I have some thermal loads, and those are going to increase some of the air change rates. So we're not always going to be down at that 6.4. We're going to be higher because you can see here I've got some moderate thermal loads that are upwards of 6 watts. That probably is roughly 6 air changes. And then I've even got some spaces, 20% of the spaces that are very high thermal load. This would be unusual, but I should try to be conservative. These would be highly dense spaces with a lot of equipment. Again, typically you wouldn't see this, but it can happen, and I did want to model it. So here I've got this involved as well, sort of a little more conservative. So when we look at that and look at the requirements for energy, you can see where that falls in the slide. We've got roughly about $600,000 a year. Obviously cooling, the heating is high. And again, keep in mind that that heating includes both the classic heating, but also includes the humidification. It's the steam humidification. So that's why that number looks larger than you might expect, and it's related to the steam humidification as well as the heating. That obviously got reheat and, of course, your fan energy. So with that in mind, you can now see the difference from the baseline case of 15 air changes and being able to go down to this, actually it's 6 and 4, the graph there is mislabeled. And as I mentioned, it's not always 6 and 4 because some of the spaces will never get down there because of the thermal load. So it's sort of a variation. But with all that in mind, you can see the energy has been significantly reduced by literally 60%. You can see that huge reduction in reheat, but also fan energy, and of course the steam and cooling. So the payback in this case was about 1.4 years, so obviously quite a significant benefit. Now, as I mentioned earlier, we also can reduce first cost because now that we've reduced the airflows quite dramatically most of the time, or almost all the time, that allows us to take advantage of that, and even with some very safe assumptions around diversity, we can still achieve very significant reductions in capital costs. So what you're seeing here is a in mind, again, we have these guidelines, and then obviously this allows a much reduced airflow rate. Hold on. just wanted to check here. Okay. So again, this requires, now we can obviously reduce these airflow air change rates. Obviously requires the use of air quality monitoring and the demand control, but again, now we can provide good air quality as well as obviously reduced energy usage. And at the same time, it allows the reduction of the capacity potentially as well. Again, the key contaminants, again, as I mentioned, were the ammonia, particulate levels, VOCs, and carbon dioxide. And as you saw, we had defined levels for that. So that, let me just sort of finish up and open it up for questions. So I think I've got a little note that the audio connection was lost, so hopefully everything came through okay. But with that, let me open up for questions, and we have a little bit of time for that now as well.
Thanks, Gordon. Can you hear me okay?
Yeah, I just saw a little note saying that I'd lost the audio connection. I don't know if that, hopefully that wasn't the case. But,
yeah, it does appear that even after we switched over, there was a couple spots where we lost you for about 5 to 10 seconds, but you bounced back in.
Okay.
So
Okay.
by and large, though, the audio quality did improve once we switched over to computer-based audio. So there are a handful of questions here. One of the questions is, has anybody in Canada already adopted this new CCAC standard yet? And if so, are you aware of where that is?
I think there's several projects going on that I mean, obviously once this came out, there started to be some projects that are now beginning to incorporate it. I should know this better. Most of my focus is outside North America, so I'm not always directly in touch with these projects. But I think there's one maybe at in Ontario province. I think it's the University of Toronto, but I'm not sure. And I think there was another one at there's 2 or 3 different projects. I'm trying to think of the names, but it will come to me. But yeah, there are things now. It's, obviously, people are holding back, waiting for this to come out. But I think there's now several projects. The University of Alberta as well. I'm trying to think now, and starts with an L. University.
Lethbridge?
Anyway. Yeah. What's it again? Which one?
Was it Lethbridge?
Yeah, right. I think that one has one going on as well.
Okay.
So yeah, so it's beginning now to be incorporated. Obviously, there's a little bit of people waiting for it to come out.
Right. Yeah, there's been quite a bit of anticipation in the marketplace. One of the other questions we have here is, you spoke about the 3 approaches to ventilation within the CCAC guideline, and you outlined do they apply? The question is, do they apply to all spaces that animals are housed?
Yeah. That's a good question. So they apply, the way this criteria is applied, the way, this is not new, it's just this the way CCC has always viewed this, is that any space that could have an animal, even for a very short period of time, falls under these requirements. So in other words, let's say you've got a classic lab space, but at times they may want to bring in like a single cage with a single animal into that space to do some monitoring of the animal or something. That means that space then falls under this criteria. So any space that may have an animal that could have an animal in it, even if it's just a single cage sitting on the bench top for an hour, has to fall under this guideline. So and it obviously comes so that's sort of, it's not just the holding rooms. It's really any room that could have an animal for even a short period of time.
Would that include a corridor or a circulation space?
Good question. I think that's the case as well. I mean, it's. I would expect that would be the case, and that's. I think so, but I'm not 100% positive. But I think that's the case. It's.
Okay.
I think that basically you'd look at where the animals would go, and then because that typically, obviously, animal corridors are covered in an animal space, and in a vivarium, and I would imagine that would cover, if you bring it outside the area, it would cover that as well.
Okay. There was another question about differential measurement, but I think it may have been posed before you explained the difference, and so, or you explained or defined that definition. But maybe for those listening, if you could explain again the definition of a differential measurement for CCAC.
Right. So Sure, definitely. So I think what we're talking about here is that we're typically comparing it to supply air. So really what we're trying to do in these rooms is we're trying to understand what is the generation, of these different contaminants. In other words, we don't really care so much about what's happening outside. I mean, obviously it's important. We don't want to have bad air coming into the space, but the purpose of the high airflow rates is to dilute the contaminants that are generated in the space itself. So to understand what the level of that contaminant is that's generated in the space, you have to look at the air going in as a source of clean air. Then we look at the air going out, which is obviously the dirty air. Then we look at the difference. So that's really what the committee was trying to get at is obviously you do want to, there's some maximum levels, and we do lay out what we expect is the clean air for supply, but at times things can happen in the supply, and that's understood, but really what we're trying to control directly is the space generated contaminants, and that's determined by this differential measurement.
Okay, thank you for that. There's a couple other questions that I had as you were speaking. One of them was, I found it really interesting, the idea of the feedback loop that demand-based ventilation, or at least IEQ monitoring, can have into operations and the use of PPE by staff. And, it seems to me that because now facilities are moving to continuous monitoring, there's a capture on information that wasn't addressed, or even, there was a lack of awareness in the past. So is that seen as a definite benefit by, let's call it the editors or the authors of the CCAC guidelines?
Yes, definitely. I mean, that was really the point here is that, again, as I mentioned in there, that there's the committee sort of recommending that even if you're not reducing airflow, there's still benefits to, and it sort of encourages, it can't require it, but it encourages people to consider air quality monitoring. Again, maybe not for every, the ones we're talking about here, but at least some level of IQ monitoring, because, as you said, there are benefits now. People may have not realized the level of contaminant that was occurring within their space, or it could be around. It could be that they thought there was contaminants that were there, and they maybe were applying measures that maybe weren't necessary. So the idea is to get some real information. I mean, that's we can't do much without data. Once we have the data, we can make informed decisions about it, and that's really what I think we're getting. It's not just early in vivariums. I mean, I think with the advent of things like the well standard and the reset standard that are out there, there's becoming a more and greater awareness of air quality and the need for monitoring to understand what's happening and then take appropriate action. So yes, I think the committee was very positive around the benefits of providing air quality monitoring based on what you could then use it for proactive measures and basically providing the right amount of protection for people.
Fair enough. There was something that you spoke about early in the presentation. It was displaying the particulate counts during cage change procedures in various rooms, and the spike in particulate counts in those rooms. And it made me think, as you finished up your presentation, about demand controlled ventilation and equipment sizing, and the potential for reducing first costs, that there has to be a connection between procedural timings and the goal towards reducing equipment sizing, because of that exact topic or that potential reason. For instance, if the goal in the design of a new animal facility is to reduce the HVAC equipment sizing to reduce first costs, then the staff move into the facility and they proceed to go room to room to room on a given day of any week and create tons of particulate. Then you're causing a one-time event once a week or once a month where you're tasking that system. So is there Any thoughts in your mind about how that can be mitigated, or how design teams might think about procedural SOPs or practice versus design?
Well, again, I think it's, again, just moving into a space, you're not going to, we're not talking about clean room conditions here typically. So, I mean, it's really, you're creating, pretty, significant impact to be able to need the airflow, which again can happen. I mean, obviously when they're cleaning the rooms that occurs, but to your point, I think, some thought is required here, but we're not, it's not getting that crazy here. I mean, obviously if someone's cleaning it, you're not going to have every room being cleaned at the same time. So some of that is, obviously we need to think about it, but realistically, and again, when I look at the data, I see the same thing that, again, it's only a few percent of the time, and you don't see like all the rooms going high. It's just like one here, one there, and you can see in the graph that I was showing you that they were cleaning one, then the colors changed, reflecting the fact that different rooms were sequentially being controlled or being cleaned.
Right.
The point here is that they do some work, the room basically cleans up pretty quickly, and then they move to the next room, and then that cleans up quickly. So I mean, obviously if there was something they were doing which was some gross effect that is occurring in all the spaces, but that's, again, I don't see it. I don't see that stuff occurring. So I think unless they're doing something with some very unique procedures,
right, so
shouldn't have to worry too much.
It was because of the ramping up of the air change rates in a room where they're doing some cleaning or they're changing cages. You're saying that the system would respond immediately, and the diversity of the effect wouldn't really impact the sizing of the system necessarily, unless they were doing something really unusual.
Right. In other words, typically the way to think about it is you've got a fair number of rooms. And again, obviously if you had a room per HVAC system, like a little air handler per room, then there's no diversity. But the assumption here is you've got 20, 30, 50 rooms on an air handler, so now there's some diversity. And these are things that typically you use something called the Hunter's curve or the binomial theorem. It's like, to use a simple analogy, it's like how you design plumbing for flushing a toilet. I mean, yes, when you flush a toilet, you got a lot of requirements, but not all toilets are going to get flushed at the same time. I mean, yes, it could happen, but it's very rare. And again, the larger the number of rooms, let's say, on an air handler, again, that gets more of an averaging effect. So there's actually it's a mathematical equation. It's called the binomial theorem, and the idea is that typically you would set it up for some level of confidence. I mean, you'd say, hey, I want to be confident to 99.9%, and I'm never going to exceed X level. So you say, if I have events occurring every 1% of the time or 5% of the time, you can then set it up in the binomial theorem. We'll say, oh, okay, for 20 rooms, the worst case situation to 99.9% of the time will be 4 rooms. And then, so based on that, you can design for 4 rooms at full flow and the rest of the rooms at a reduced flow, and set your capacity for that. And you can get more conservative. You can set 99.99%. But again, when you think about this, I mean, we don't design buildings for the worst case 100%, design conditions. We set it up for like 99% and realize that, yeah, sometimes you're going to get a little bit warmer or cooler in those spaces. Maybe Vivariums you might go a little higher, maybe 99.5, but you're not going to 100%. So we have to just keep that in mind in terms of this and apply things appropriately.
Excellent. Well, thank you for that. There's one other question. It's about the monitoring of the air quality. Where does this typically take place? Is it generally right, at the room, at the exhaust, or is it, at, let's call it, the point of exhaust of the building?
No, it's definitely at the room exhaust. I mean, the best place is the room exhaust. The other thing we just want to make sure, like in labs, you don't want to measure the fume exhaust in for Vivarium. You don't want to measure the rack exhaust. So you just want to look at the room exhaust. Again, that's the room exhaust coming out of the space. If for some reason you can't, because let's say the room exhaust is immediately combined with like rack exhaust, then we would run for like a wall mount or sensor in the space or a pickup point. I mean, so that then you can basically basically monitor that. But most likely, you can just use the room exhaust. It will work fine, and that's typically what's done.
Perfect. Okay.
Yep.
Well, we're at the top of the hour, and that's all of the questions we had, Gordon. So, on behalf of SLCan, thank you very much for presenting today. It was really, really helpful and informative, and we've recorded the session for members who weren't able to attend today, so we'll have that up for our members. But again, thank you very much for your time today. Appreciate it.
Oh, my pleasure. Yep, thank you.
All right. Thank you, and
Bye-bye now.
have a great day. Take care.
Hey, thanks. Bye-bye.